Hey guys, today we're looking at 6.4's notes, which is all about graphing exponential and logarithmic functions and their transformations. I'm not going to bother with these equations. We already know what exponential equations look like. We know our number is a base and our exponent is a variable. Logarithmic functions, obviously we've been dealing with those for the last couple of days, and we know what transformations are. So I'm just going to jump into just reminding ourselves of what our different transformations are, and then take a look at a couple of different examples for each. So here is our trusty old transformation table here, where each row is a different type of transformation. It shows you what it looks like in function notation, and then it gives you some examples of what it would look like. In this case, this front side of our notes is exponential functions. So again, our number is a base here. They're giving the example of 4 to the x power being my parent graph, and then all these different transformations happening are just our shifts, reflections, stretches or shrinks from that original function 4 to the x power. For the first one that we're doing, I want to use the function, because we haven't done one like this yet. I want to use our natural number. So I want to use the function f of x equals e to the x power for our parent graph. And then from there, I want to use g of x, our transformed function, as e to the x minus 4 power. Now, usually, most of the time, what you're going to be given is just this g to the x power. So it's just going to give you e to the x minus 4. When we're going through and trying to graph these, it's easiest for us in these cases to be able to graph my parent graph first and then just do the transformation afterwards. Because in most of the time, our instructions are going to be to graph both the parent graph and the transformed function. So we're going to have to do that anyway. So for my parent graph, the way that we do this, we've got to make our x work y table. We're going to have to evaluate for an exponential. We have to evaluate 3 different x values. We need 3 points to be able to evaluate them. And the x values that we use are based on what our base is. So this base e, if you need to look in your if you need to check yourself, remind yourself if you forget what your base e is, when we evaluate that, our actual number for E is 2.78 something, or 718. So it's definitely bigger than 1. They're not going to be nice numbers either way, but in our case where it's exponential growth, because our base is bigger than 1, we want to use 0, positive 1, and positive 2 for our exponents. That's going to give us the nicest numbers that are possible for our function. So as I'm going through here, so my equation is e to the x power, so I'm going to do e to the 0, e to the first, and then e squared. And you've got the option on your calculator to do this. I think most of the time, if you hit the E button on your calculator, it's going to pop up with something like that, where it does the little exponent caret and then opens a parenthesis. You'll put in whatever the exponent is in there, and that'll be good to go. So without having to use a calculator, e to the 0 power, we know that's going to be positive 1. That's why we use 0 all the time. It's going to give us a nice whole number regardless. E to the first, again, we'll just approximate since we're going to have to guesstimate for the graph anyway. If you do e to the first power, it's 2.7, and then e squared is 7.4. So those are my coordinates. I'll use those to plot the points. So 0, 1, 1, 2.7, and then 2, 1, 2, 3, 4, 5, 6, 7, almost 7.5. Now the other thing that I forgot to mention here is that we have our asymptote. For an exponential, if we don't have, our asymptote is always 0 when we are just dealing with their parent graphs. So e to the x power, as long as there's no other shifts happening, our asymptote is 0. And remember, our asymptote, that imaginary line that my graph gets really, really close to but isn't actually hit. It can't get through it. It kind of acts like a force field or a boundary for my function. Because now looking at how my graph is curved, I have my graph goes through those points, and then it gets close to my force field, but kind of follows along in that same path. So that's my parent graph. That's f of x. Now, looking at g of x, in red here, I'm subtracting 4 up in the exponent. So in this case, an exponential is my function. So if I'm subtracting 4 in my function inside, that should be a horizontal movement. And if you forgot, you can take a look right up here. 4 to the x minus 3 power told us we shifted 3 units to the right. So here, if we're doing e to the x minus 4, that means that we should be shifting right 4. And that's how we'll get our g of x function. So all I have to do is shift 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I'm not shifting up or down at all, so my asymptote is still right there at 0, 0, or sorry, at 0. And then I'm just gonna follow along, go through my points, level off, and going in that same direction. So literally just shifted 4 to the right. Okay, hopping over here to our second example of exponentials. The two functions that I want to deal with for this one, our parent graph is going to be 1/3 to the x power. And then for g of x, I want to do 1/3 to the negative x minus 4. So for my parent graph, my exponential base is 1/3. It's between 0 and 1. This is an exponential decay function. So for my x work y table, there we go, 1, 2, 3 of them. Since we're dealing with 1/3 to the x power, the nice clean numbers that we'll get, 0 obviously will still give us a nice clean number, but because we're dealing with a fraction, we want negatives because that's going to flip that fraction over and give us a nice whole number. So 0, -1, and -2 should be the 3 points that I'm using on an exponential decay function. And that's always the case, not just because this is 1/3, but because it's a decay function, our base was smaller than 1, we want to use our negatives. Because now what's going to happen, 1/3 to the 0, well that still gives us 1, but 1/3 to the negative first makes this 3/1 to the positive first, because of exponent rules, right? Negatives flip them over. So that gives me 3. And then 1/3 to the negative second is the same thing as 3/1 to the positive second. So 3 squared is 9. So still have my asymptote at 0, 0, comma 1, -1, comma 1, 2, 3, and then -2, comma 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. So we got, there we go. There's our nice function. That's f of x. That's our original parent graph. Now, looking at what's happening to g of x, we have two different things happening. We have a negative in our exponent, and we have a -4 on the outside. So our two different transformations, we are doing a horizontal reflection. That's that negative in my exponent. Horizontal reflection. And then that -4 is a shift down 4. Now, in these transformations, in these exponentials, what you have to make sure you remember, I'll put a little note here, an asterisk, we always reflect or stretch/shrink first. So when we're dealing with things that are happening with multiple different transformations, if you have a reflection, a stretch, or a shrink, you have to do those things first, and then you do your shifting up, down, left, or right. Translation should always be the last thing that you do. So in this case, what we have to do is reflect our points horizontally and then go down 4. So you can do this kind of 2 separate times. You can try and do this simultaneously. So reflecting horizontally means we're just going to count over from the y-axis, however many units it takes to get there. We go do the same thing, and then I'm just going to shift down 4. So for this first point, I'm going to circle it in yellow here. For this point that I'm going to be moving, if I reflected over the y-axis, that it would put it right here. But then I still have to shift it down 4 units. So down 1, 2, 3, 4 is this point right here, and I'm going to do that in red. So 1, 2, 3, 4, and that's my final point. So the yellow is going to be kind of our reflection part, and then we're going to shift down and kind of finalize it in red. So for this next one, for what was originally -1, 3, reflecting it over the y-axis would put it right there. But then we have to shift down 1, 2, 3, 4. That's that point now. And then last but not least, this third point, I can't reflect it over the y-axis because it's on the y-axis. So all I need to do is shift that down 1, 2, 3, 4, and that's my point right there. The last thing with these, since we have a vertical shift happening, that means my asymptote also has to get shifted. So it has to get shifted down 4 units. So down here at -4 is where I should have my asymptote happening now, because that's 4 units below where it started. So that yellow stuff is just kind of scratch work. Our actual function are these 3 red points and then our red asymptote. So we've reflected horizontally and shifted down 4. All right. So on the back side, we've got our logarithmic functions that we're dealing with now. So for our logs, same idea. I think it's a little bit easier with our logs to keep track of whether it's inside or outside, because if it's an inside transform, like a horizontal shift or stretch or reflection, is going to be locked inside with parentheses, because our function is our log. So if we're in parentheses, that's inside our function. But all the same rules we've been doing. Addition, subtraction is a shift. Multiplication is a stretch or a shrink. A negative is a reflection. Inside is horizontal, outside is vertical. So for our 2 examples here that we're going to do, we've got f of x. Here we go. For this first one, we've got f of x is log base 1/2 of x. And then our transformed graph g of x is going to be log base 1/2 of x plus 4. So remember, like we did yesterday on 6.3 part 2, not yesterday, but in our previous notes, when we're going through and graphing these logarithms, it is going to be much easier for us to rearrange it into exponential form. And remember that this is the same, f of x is the same thing as y. So if I'm rearranging this equation, this is the same equation as 1/2 to the y power equals x. That's the same thing. So instead of trying to graph a new log, it's the same thing as we just did in the front side. I have an exponential. I'm going to try and evaluate those different points. So if I go here to my table, now be careful, because now my exponent that I'm choosing is my y value, and the x value that I'm getting back out is my output. So I'm choosing y values and getting x values. So that's a little bit of a change of pace. But we're still doing the same thing. We're still picking out 3 x value, or 3 inputs, which in this case, since my base is 1/2, we should be using those negatives. So 0, -1, -2, because we've got 1/2 to the y power is what we're evaluating. So 1/2 to the 0, 1/2 to the -1st, 1/2 to the -2nd, should give me 1, 2, and 4. Now be careful, because when I have my points, I still have to graph them x comma y. So my coordinates here would be 1, 0, 2, -1, and 4, -2. So we've got 1, 0 is right there, 2, -1 is right there, and then 4, -2 is right there. So what happens, like we saw on 6.3 part 1 or part 2, we now have a vertical asymptote instead of a horizontal one. And there we go. Follows the asymptote along. There's my original parent graph for g of x, or for f of x. G of x is +4 on the inside, so that tells us we should be shifting left 4 for our transformation. So all we have to do is take those 3 points and our asymptote and shift it horizontally to the left 4. So because it is a horizontal shift and our asymptote is going to move, we got 1, 2, 3, 4. And I'm just going to go ahead and shoom, 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 shoom. And I count left 4 for my 3 points. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then again, just follow my asymptote. There we go. There is g of x in red. All right, last but not least, for our last example here, we've got f of x equals log base 4 of x. And then for g of x, we are doing 1/2 log base 4 of x minus 8. So first and foremost, this is 4 to the y power. 4 to the y equals x. So our y work x table, we've got 0, 1, and 2. 4 to the y. So 4 to the 0 is 1. 4 to the first is 4. 4 squared is 16. Now that's going to be an issue for us because 16 is off my grid. But that's all right. We'll leave it as is because it'll change in a little bit here. So vertical asymptote at 0 still, so I'm still hunky-dory there. Again, 1, 0, 1, 2, 3, 4, 1, and then 16. Okay, so that's 10, 11, 12, 13, 14, 15, 16, 2 is about right there. It's about right there. So I'm going to go ahead and there we go. There is my original f of x, my parent graph. Now, with my transformed graph, I have two different things happening. I have my 1/2 out in front, so this is going to be a vertical shrink by 1/2. So that's transformation number 1. And then it's also going to be shifted down 8. So that's what that minus 8 is telling me. So again, I'm going to go ahead and kind of do the same thing we're doing before. I'm going to circle in yellow, do our initial our shrink in this case, and then shift it where it needed to be. So for 1, 0, shrinking it by 1/2, it's already on the x-axis, so it can't shrink any further vertically. So all I have to do for that point is shift it down 8. 1, 2, 3, 4, 5, 6, that's 5, 6, 7, 8. There's that point right there. For this point right here, for what was originally 4, 1, shrinking it by 1/2 would be putting it at 4, 1/2. So I have to go down 8 units from there, which would be right here, just counting down 8. And then our last one here, 16, 2. Well, cutting it in half would make it 16, 1. So then if I shift it down 8, it would be right here, down 8 units. So much more harsh, I guess, much more flat. But that would be what my last graph looks like. Okay. So that is it for today. I forgot to add this down here at the bottom. Your homework is page 322 and 323. You guys are doing number 4 through 40, every other even. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.